In this video, we will learn about the KNN artificial intelligence model called K-nearest neighbor and examine the coding file directly. When explaining the KNN model, a proverb of birds of a feather flock together is often quoted. It means that similar entities or objects tend to gather together based on their similar characteristics or attributes, and predictions are made based on the attributes of neighboring data. In other words, KNN is a distance-based analysis model, where K represents the number of neighboring data points. Therefore, using the closest K data points, the majority pattern is followed. The closer the distance, the more similar they are considered to be. Based on this concept, the KNN model can be used for classification and regression analysis purposes. If we look at this illustration below, in the context of classification prediction, for the new yellow data point, we want to predict whether it is closer to the red or blue points. If we can set K to 3, among the closest 3 data points, 2 of them are red, so it will be predicted as red. On the other hand, if we set K to 5, among the closest 5 data points, 2 are red and 3 are blue, so the majority is blue, and it will be classified as blue. KNN can also be used for regression. For example, if K is set to 3, we take the average of the closest 3 values, which are 10, 20, and 30, resulting in a prediction of 20. Similarly, if K is set to 5, the average of the closest 5 values, which is 10, 20, 30, 40, and 50, results in a prediction of 50. KNN is a distance-based model, so it requires a method to measure the distance between data points. There are several distance measurement methods, but let's explain the Euclidean distance and Manhattan distance out of them. First, the Euclidean distance is the most commonly used distance measurement method in KNN. It measures the closest distance between points. You can think of it as the Pythagorean theorem we learned in school. For example, in a two-dimensional plane, if we have 2 different points A and B, we calculate the difference between them, take the sum of squares, and then take the square root. If the coordinates of point A are 1, 1, and the coordinates of point B are 5, 5, we can calculate the distance as the square root of 32. The Manhattan distance measurement represents the distance traveled along the x and y axes, rather than the straight line distance between points. In other words, it is often called the taxicab distance, because it reflects the distance covered by a taxi traveling through the streets of Manhattan, where the roads form a grid-like pattern. The calculation method for the Manhattan distance involves finding the absolute differences in the coordinates of 2 different points and summing them. For example, if we have 2 different points A and B, and the coordinates of point A are 1, 1, while the coordinates of point B are 5, 5, the Manhattan distance would be 8. Manhattan distance is known as L1 distance, while Euclidean distance is referred to as L2 distance. We will explain these terms in more detail in future discussions, particularly in the context of regularization methods to address overfitting in deep learning. This slide shows the screen for coding KNN model. The Jupyter Notebook file is available on GitHub, so you can download it and run it yourself. Similar to the previous decision tree and random forest models, we start by importing the necessary libraries such as NumPy, Pandas, and Train Test Split. Then, we load the Excel dataset of Iris. Next, we assign X and Y, representing the features and the target variable respectively. After that, we split the data into training and testing datasets, following an 8:2 ratio. To build the KNN classification model, we need to import the neighbors classifier library. If you encounter an error stating that the library is not available, you can install it using the pip install command. After importing the library, we create a KNN model with 5 neighbors and store it in the KNN variable. Here, 5 represents the number of nearest neighbors, which is a hyperparameter. In this case, we create a KNN model using 5 nearest neighbors. Next, we train the model using the X training and Y training data and evaluate its accuracy. The results show that the model has an accuracy of 98.3% on the training data, indicating that it predicts the flower species correctly. When applied to the testing data, The accuracy is 93.3%, demonstrating that the model predicts the iris flower species with an accuracy of 93.3%. Lastly, as explained in the random forest video, we can use a for loop to create a simple code that checks whether the actual species and the predicted species match or not. As shown in this slide, when the actual and predicted values match, it is displayed as true, and when they do not match, it is displayed as false.